Are you guys see my full screen?
Yes.
Sure, thank you. Well, before presenting myself, I would like to start saying thank you very much for the members of the scientific committee. I'm pretty proud to have the participation of each one of you in this highly skilled PhD committee. Thank you all very much. And then I would like to thank all the institutes, agencies, private companies, research networks, and so forth that contributed and supported the developments of this doctorate in the last 4 years. So thank you for this university, Federal University of Pará, the Geoscience Institute, the scientific funding agencies, CNP, KIL, and CAPES, the Map Biomas Network, the Instituto Vale, and SOVD. By the way, the last one, SOVD, is one of the most unusual outcomes of this doctorate. It's a private scientific company developed because of the things we've managed to create during this doctorate. I'm Cesar Guerrero Diniz, and the advisor is Dr. Pedro Balfe. Let's start. Well, the title of this presentation is 3 Decades of Changes in the Brazilian Coastal Plain, the Status of Mangroves, Aquaculture, and Saltculture using Landsat Time Series and Machine Learning Techniques. The summary of this presentation is structured as forth. We're going to start with the objectives, a bit of theoretical background, methods, results, structured in 2 different articles, one already published and one already accepted, the conclusions, and then future developments. From this point on, this bar here will highlight automatically which section of the work I'm talking about. So first things first, let's start with the thesis objectives. The main one was to detect and map land use and land cover changes associated with mangrove vegetation and aquaculture/saline activity in the Brazilian coastal zone, from this point on, named BCZ, in the period of 1985 to 2019. The specific objectives are pretty straightforward and are composed of 3 main elements. Create and verify the robustness of a spectral index, specially designed to better discriminate mangrove forest from the surrounding vegetation. Detect the changes between the specified time ranges and analyze increase and/or reduction of mangrove areas. Similarly to the specific objective 3, which is to detect but analyze also increase and/or reduction of aquaculture or saline activity. No matter what is the class you're interested on, when you're classifying a huge temporal span of orbital data, regardless of the satellite you're using, we have always 4 main constraints. The first is, are annual cloud-free composites possible to be created? How is the Landsat data distributed between 1985 to 2019? Is it homogeneous, or there's some heterogeneity associated to that? The third, and by far the most important one, is in which information domain are the key attributes that allows you to distinguish between the desired classes. And fourth, if we are going to achieve different domains and perform a multi-domain analysis, is Google Earth Engine capable of being the base for this computational development? Those are the 4 main constraints. I hope at the end of this presentation, everyone will have an answer to. In terms of spatial distribution, we are going to work always inside what we call BCZ, Brazilian Coastal Zone, which in Brazil is defined as law by a decree, in this case, decree number 5300 from 2004. This decree not only defines the concept of a coastal zone used in Brazil, but also attributes to the Brazilian Institute of Geography and Statistics the responsibility for officially mapping the coastal marine system in Brazil. And that is the layer, the spatial distribution that we are using to do our first subset in our data stack. Everything from the Landsat perspective is subsetted to the BCZ according to its definition and cartographic representation imprinted by the IBGE. Okay, once subsetted, we need to understand which domain of information is the one that is capable of allowing us to distinguish between the interested class we are focusing in separating. The first thing is, well, in remote sensing, we have three main domains: time, space, spectrum. In this picture here, the temporal domain is related to the variation in the time acquisition of each Landsat scene. And we are showing temporal variation by this depthening of this z-axis. The spatial domain is related to spatial attributes and how they are interconnected to one another, each pixel of this X and Y dimension here. So this is the spatial domain. It relates to the distribution of the pixels and how they relate to one another. The third is the spectrum domain. In here, we have the physics of the remote sensing helm, the quantity of bands in your sensor and the bandwidth of each spectral band together compute what we call spectral domain. So each target will have a specific behavior to each one of the bands associated to the image. Here's the spectral domain. Great. Now that we know about this three main domains of information, we need to analyze which one of the domains are responsible for separating the classes we wish for. We ain't gonna illustrate how mangrove is dissociated, because classically in the scientific literature there is already a vast documentation showing that the biophysics configuration of the mangrove strata makes it highly differentiable in terms of spectrality among its neighbor composites. But when we talk about water, things get a bit dirty. Water, and we want to separate aqua salt culture from everything else that may be composed by water, then the things are a bit different. In green, we have samples that were thrown over the ocean, in red, over the river main channel, and in dark blue, quite violet, over artificial ponds filled with water. Irrelevant if it's salt production or aquaculture. In here, everything will be the same. Artificial coastal ponds. When we analyze all those three targets in terms of a spectral distinction between them, it's clear that the spectral domain fails miserably to dissociate one target from another. So the spectral domain ain't the domain you wish for when separating aquaculture from the rest. Similarly, if we analyze the temporal domain as aquaculture and saltculture activities in Brazil are quite traditional, it's expected that there will be some aquaculture, saltculture quite consolidated in time, others will be quite new. But if we compare the temporal variation of each water surface, that's exactly what this map is doing. Solid blue means frequently occurrence of water surface. Dark light blue is occasional occurrence of water pixels. If we compare the water samples, the river samples, and the aquaculture ones, we're going to see that the time or the temporal domain starts to allow me some differentiation, but it doesn't guarantee I'm capable of distinguishing one thing from another. There's still aquaculture ponds, highly frequent through time, as it is the ocean and the river. So I need another domain. That's why this picture is here. To distinguish what is aquaculture from what is natural water surface, we are going to use its spatial attributes. Aqua/salt prediction means generation of artificial ponds that are naturally square, rectangle, regularly shaped, triangle, trapezoid, and so forth. Thus, it ain't gonna be the spectrum, it ain't gonna be the time. The domain which will allow dissociation of water artificial targets for a natural one is the space. Great, we know we need the space and we know we need the spectrum. Two different domains for two different classes. Mangrove will be mapped using Brandon forest. Brandon forest is probably the most common spectral classifier from the last 2 decades. It uses three main concepts of statistical analysis. The first one is, if you're really capable of distinguishing something spectrally, then if I pick random samples and random attributes, but the target is spectrally distinct, then I will be capable of dissociating one thing from another. The Brandon forest will use a lot of decision trees. That's why it has the name of forest. Because it has a lot of decision trees, we're going to use the majority decision or aggregate every decision of every single tree, and the one that has the most frequent answer, that's the class tagged in that given pixel. Thus, Brandon forest most of the time relates to spectral difference within your classes. It needs to exist. Great. We just saw that for dissociation of artificial ponds from everything else with water, we cannot rely on spectral temporal attributes. We need to access all the domain, which is called space domain or context. To do so, we're going to use convolutional neural nets. And the word convolutional is the key word to access the context domain. In here, we are not talking about pixels, we are talking about grids and shapes that define entire objects, not solely isolated pixels. Great. Let's understand what is convolution. Convolution is a different name for something we all heard or saw once in our life. I don't know why, but someone decided that computationally it's better to name this convolution. But this is a moving canal, canal filter, moving window, and so forth. What the convolution does, well, I need an input, and I need a moving window. This moving window is another matrix, similar to the input, but a bit smaller. What we are going to do is to mathematically operate the numbers while sliding this window through the original matrix. And by doing so, I'm grabbing information of my neighboring pixels, of the vicinity of the pixels, and I'm computing this in an aggregated manner. And here, this input times this kernel equals, for the first position of the grid, the sum, the aggregate sum of 12, and so forth. What is interesting here? The input has 1, 2, 3, 4, 5 columns per 5 rows. The kernel is a 3x3 kernel, and the result is a 3x3 result. So we have a problem, a mathematical one. If the input is 5x5 and the output is 3x3, we are losing information and losing the ability to locate ourselves in space, because the columns and the rows are not in the same size anymore. So we need to compensate that. While acquiring context vicinity information, I will need to have an output that matches exactly the same size of the input. And that's why we chose the UNet classifier from the family of convolution neural net. What the UNet does is exactly what we wanted a classifier to do. It grabs an image, and it wasn't created for remote sensing analysis. It was created for biomedical analysis, my ability to locate damaged cells and so forth. And it does this. A sequence of convolutions. We already saw what is a convolution. So we're gonna extract contextual information while reducing the X and Y dimension of the image. Contextual information is added, although we reduce size of the input, no problem. Add more contextual information and so forth. It reaches a point that enough contextual information is already added as bands, as layers of this input image. Then it's time to restore the size of the original input. And to restore what mathematically was caused by convolution, we apply another mathematical tool called transposed convolution. So what the traditional convolution does, the transposed convolution undoes. And then at the end of the U-shaped algorithm, that's why it's called UNet, we have all the context attributes extracted from the contraction moment and all the spatial properties restored by the expansion moment. That's exactly why we chose the UNet. So understanding the domain of information is the key to understand which classifier to apply. Basically, during this flowchart, we are going to see the use of three different algorithms. One unsupervised for different strategy, different use, and two supervised, the ensemble ones and the neural network ones, in this case, UNet, a CNN, and random forest. Great, we are interested in two classes, but let's understand visually what we are calling two classes. Class one, mangrove vegetation, not mangrove ecosystem. The mangrove word can be related to ecosystem, to a type of vegetation, or to geobotanical units, and so forth. The ecosystem is constituted by the salt flats, by the apicans, by the sandy exposure on the edge of the mangrove, and so forth. We are mapping mangrove vegetation like this. Great. This is important for the discussion when it's time to come. And this is a picture of mangrove here in Pará, in the north of Brazil. This is Curaçao in Pará. All these huge trees here are mangrove. and this is the traditional root system of a mangrove tree. Great, what is aquaculture slash saltculture? Artificial coastal ponds. We are not dissociating what is used for salt production and what is used for any other thing production. It might be shrimp, it might be fish, it might be any other thing. It's an aquaculture. We are not dissociating it from salt extraction. This is how we classify it. Without classification, classified by unit. That was the first prototype. From this point on, we improved a bit. And this is a beautiful photograph from Renato Stockler for National Geographic documentarist. This is the salt terminal of Areia Branca in Rio Grande do Norte. This is the processing flow. Basically, there are 4 steps. In blue, image processing stuff. In green, training data set generation. In yellow, classification and post-classification. In red, integration and accuracy assessment. Those are the basic steps of any digital classification of volatile data. What we do is we grab the Landsat collection from 1985 to 2018 for mangrove or 2019 for aquaculture. We produce the cloud-free composites. We do the subset using the geographic layer from the IBGA plus the SRTM topographic information. We create all the spectral indices we need, and we select all the bands from the Landsat we wish to select. Then this image processing step is concluded. We start the process of grabbing samples. Unfortunately, for aquaculture slash saltculture, there is no national scale available reference map. If it is available somewhere, it is not publicly available. We could not find anything. In terms of mangrove maps, then there is a bunch of other research work from other specialists, which was really helpful. We're going to use the reference maps if they are available. We're going to set a training region based on the unsupervised classifier I've mentioned. The unsupervised classifier here will reduce the dimensionality for looking for samples of that given class. We do the sample balance, and in here, it takes different directions. If it's mangrove-related stuff, random forest. If it's aquaculture-related stuff, TensorFlow. And TensorFlow, it's a library, but we ain't going to talk of computational details in this moment. Once everything is classified, we do a set of post-classification filters. I'll put the map, integrate, evaluate the accuracy assessment of both products, and give it all a public availability through the internet. Those are the 4 boxes that are slightly different depending if it is aquaculture or mangrove. Okay, the first step was, let's create cloud-free composites. 10, 15 years ago, it wouldn't be that easy to create a cloud-free composite, but thanks to Google Earth Engine and its geospatial capabilities, this is quite easy. 8 lines of code. We can grab one single image that was like this, and we can, using information from all the images, produce what we call statistical reduced slices, median reducer, together with a quality band, a mask coming from NASA or USGS, saying where the clouds are. And we can produce this within a few minutes of processing. So thank you very much, Google Earth Engine. A huge part of the problems within optical analysis comes from Earth, from cloud noisy behavior. So this helps pretty much to reduce a bunch of problems. Great. as I mentioned, I need to understand how is the distribution of Landsat data through 1985 to 2019. And as expected, the nearer we go to the past, the nearer we go to 1985, the less data we have available. And this is quite easy to understand, because flying above our heads, we have today much more capability of producing image, and we have more than one satellite. In here, in 1985, the ability to store data coming from the satellite wasn't that good, and also the quantity of satellites from the Landsat family flying above our heads were reduced to 1. That's what is causing this heterogeneous distribution of clear pixels to be processed. Great. We already have the cloud-free composite. We already evaluated its distribution through time. Now, we are going to, using class variability analysis and cloud persistence based on Yarrow-Schaffer-Novelli work, we're gonna subdivide, longitudinally speaking, subdivide the Brazilian coastal zone into sectors. Sector 1, Amapá, Sector 2, Marajó Island, and so forth. From north to south, we have 7 sectors. It's important to highlight that from this point here to the extreme south of Brazil, there is no mangrove existing there. That's the Laguna municipality, and the main controller of the non-existence of mangrove is basically the temperature. If it gets too cold, then no mangrove shall resist to that. Main attributes, remember, 2 classifier, one operates in the spectral domain, the other operates in the context domain. So some important spectral attributes. We can have any of the classical Landsat bands we wish. This is a RGB composition 654 Landsat 8. So this is how it looks like in this false color composite. In here, there's a bunch of things. There's a bit of mangrove, a bit of ocean, river, aquaculture, so forth. For trained eyes, it's maybe easy to differentiate where's the mangrove, but for untrained eyes, it's not that easy. Here's the NDVI. It's a traditional, pretty classical spectral index from the remote sensing area. It dissociates pretty well not vegetation from vegetated pixels. And here is the same approach. It's a normalized difference index, but to dissociate water. It's called modified normalized difference water index. And it dissociates pretty well water pixels from non-water pixels. And that's the third and one of the specific objectives of this PhD. The MMRI stands for Modular Mangrove Recognition Index, and it tries to dissociate mangrove vegetation from the surrounding vegetation. We're going to see in more details how it works. Great. So I have my mosaics free of clouds. I've extracted my attributes. I have all the spectral index I wish. Let's see if I have enough reference data to help me, to guide me in the process of acquiring samples. So for mangrove, we have a bunch, really a huge quantity of references to stating where, at least somewhere in time, our mangroves are. We have the atlas from the Chico Mendes Institute. It's Landsat interpretation, visual interpretation of 2013 data. We have global data sets from Global Mangrove Forest Watch and from NASA, from Dr. Jury, actually, the first global mapping of mangrove, available publicly for a quite huge variety of years. And we have, unfortunately, for aquaculture and saliculture ponds, only text documents without shapefiles publicly available. So it doesn't help that much to automatize the process of grabbing samples. And also we have a bunch of local papers on mangrove and aqua saliculture distribution in Brazil. Good. Now let's understand step by step what happens from the moment we acquire a cloud-free mosaic to the moment we classify. This is in the coast of Venezuela, and the idea is if the method we are creating is good enough, it has to work outside or inside Brazil, and we are testing in the coast of Venezuela. So this is a cloud-free mosaic based on the median reducer plus the quality band strategy. This is the mangrove, the modular mangrove recognition index computed over the same region. Then we're talking about mangrove. There are a bunch of references. We use, for instance, Dr. Jury Chandra global mapping to say, well, we agree. I'm not interested in how much we agree right now. I'm just interested in, well, there is possibly mangrove there. Take this reference, add a buffer, a huge one, like 50-kilometer buffer, do a clustering analysis on top of that, and then you locate the mangrove cluster. Over the mangrove cluster and grouping all the other clusters, we throw 1,000 samples per class, per sector, per year, which means 1,000 sample times 2 classes, times 6 sectors, times 33 years. 400,000 samples of mangrove, non-mangrove for the entire 43 years of stacked images. And here's the random forest raw output. Great. Now we understand how the spectral temporal classifier works. Let's switch to the UNet. Here's the northeast of Brazil, and we need to start with a cloud-free composite using the same strategy, and then no reference exists. Thus, I will have to manually draw it, but I hate drawing. There isn't something in my life which I hate most than drawing. So if it is to draw, I better draw rapidly and pretty poorly. So we do a water mask using K-means, and I can poorly surround the aquaculture ponds. No matter, it's not a problem if I include non-water pixels in the polygon I've just created, because I will use the mask plus the surrounding area as an interest area to extract what we call aquaculture/saliculture samples. And that's the result of the CNN UNet classification raw product without any filter. Great. We have classified a bunch of things. But remember, the distribution of satellite data is not homogeneously distributed through the entire time span. Therefore, we need to start a chain of post-classification filters to get rid of a lot of small problems, but that we can surely tackle to make the product much better than it is in its raw state. The first thing is, if there is uneven distribution of data, I have to gap fill my classifications, looking to the future, so I can replace no data in the past, like this. So this surface here is the blue color of this surface here is data from 1985. The data from 1985 is fulfilled with holes, although I have 33 years of the data towards 1985. Thus, I can grab from some of the other years information to fill in this node data class value. And that's what we do. The blue region is mainly from 1985, but we have some chunks of pixels belonging to different years. We can do this looking to the future if we are in the past, and if we are in the top, the most recent data, we can look to the past and do similarly. Great. We have counterbalanced the problems of no data existence. Now, we filled the no data values, although in the temporal series, we have a bunch of things that may cause difficulties for automatic classifiers to tag, to categorize each pixel as the classes you're wishing for. For instance, there are problems within SLC off characteristics of the Landsat 7. There are, even if I've constricted my mosaic of cloud-free composites, there are still some areas with haze aspect that is hard to remove. Those noises can change the class it should be classified into something else. Because of that, we have temporal filters, which is pretty simple. The temporal filter is a ternary. It is a moving window that moves 3 by 3 ears, and it expects the central position of 3 consecutive ears. If the extremities of the ternary moment, T1, T3, are equal, the same class, but the center class is not, we shift the center class to match its extremities. And we apply this to both Mangrove classification and Aquiculture classification. The important thing of doing this in case of mangrove is removing noise from mangrove, because there is no possibility of a natural variation of mangrove forest become non-mangrove forest and suddenly in the other ear mangrove forest again. In the case of South Culture, even if a pond is dried up, because we need to let the pond dry up to extract the salt, for instance, it is extracted by evaporation of water. Even though, if you say it's aquaculture, salt culture, and then it gets empty, and it's salt culture again, this shift here was purely occasional. The use remained salt culture use. So we apply it into both the land cover and the land use. Great, reaching the final part of the filter. UNAT and random forest are both pixel-based classification. And by doing so, by being so a pixel-based classification, they always produce isolated pixels, the classical salt and pepper effect of the remote sensing literature. And we can remove that by applying spatial filters. In this case, we remove only isolated pixels that do not concatenate, do not connect itself to form groups of at least 10 pixels. Then it helps to remove the salt and pepper aspect of a pixel-based classification. Another important thing is that, okay, we have 33 years of data. So we have a huge temporal information, which we can use to remove a bunch of noisy and awkward classifications also. For instance, in this region here, it's a mangrove-dominated peninsula in Para. The green classes are mangrove classifications that appeared only less than 3 years out of 33 possible. So it's really sporadic. Those sporadic, not frequent, quite rare appearance of mangroves will be removed from the series. Before filtering, after filtering, much better. That's all. That's the method. Nothing to add more about the method. Let's go to the results. The results are grouped in Article 1 and Article 2. Article 1 is about the Brazilian mangrove status, 3 decades of satellite data analysis, published in April 4th, 2019. Great. The first thing that this first article focused upon is describe how we created the MMRI. So the MMRI did not pop up in my mind by magic. There is a drought difference, a normalized difference drought index that does something pretty similar, but it could have been better if it was focusing only in mangrove. What we did was basically adjust the mathematics of the drought index. So instead of aiming to dissociate drought and severe droughts, it could have been applied to coastal zone and help us to enhance the contrast of mangrove vegetation. That's what we did. NDVI minus NDWI, thus vegetation minus water. We did the same, but in the opposite constriction. And instead of using the NDWI, we are using the MNDWI. This fellow here outputs its numbers in unusual numerical domain. So we added the modulus, which forces this mathematical operation to output its numbers in the -1 to 1 limit, the classical range for spectral indexes. How it is, this is coast of Maranhão. So for untrained eyes, the mangrove index really makes it easier, intuitive to dissociate mangrove from something else. Great. This is for the coast of Para. And here you don't need the MMRI because, wow, the mangroves are so dense and they are so packed that you really don't need, but here how it is. So in green, we tend to have mangrove, and there's some sort of yellow, we tend to have other types of vegetation, but not mangrove. The pinky tends to be not vegetation, and blue, solid blue, tends to be water. And this is in the northeast of Brazil, in Bahia state, its capital, Salvador. The color composed, the spectral index. Great. At least visually, it's okay. The visual aspect of the index is good. But visually is not enough in science. We need to statistically prove what our eyes are seeing. Thus, we take, again, a global reference, and we are going to cross-compare it versus classification of mangrove, non-mangrove strata based solely in a single attribute. Each one of the index we are testing. NDVI, NDWI, CMRI, which is another mangrove index named Combined Mangrove Recognition Index, and our MMRI. So basically, after cross-comparing one to the other, we can clearly see that mangroves and non-mangrove strata are quite confused here compared to the reference, and so it does for the NDWI, CMRI, until it comes into the MMRI, which is a raw representation, but it's visually really quite close to the reference. No matter which metric attribute you use, if it's kappa, overall agreement, commission or omission, no matter what, our analysis within the cross comparison presents us better attributes than any other. Even the Bhattacharya coefficient shows that comparing our non-mangrove strata to the mangrove strata, they are statistically divergent, dissociated, while others are not. Good, that's the annual mangrove area variation from 1985 to 2008. Attention, careful, please do not rush the interpretation that from 1985 to 2018, the mangroves in the Brazilian coast have all experienced regeneration processes. This is not true. That's not the precise analysis it should be done by looking to this graph. Instead of saying that, pay attention that there is something like two periods. One is the first period, the second period. They are different in terms of how they behave within the trend of accumulating or losing mangrove cover. Let's see this in a better picture. And here in the top graphic, I have the national trend showing this upward momentum, but I have also the quantity of images available to each period, and I've also sliced the periods in two and then recalculated the trend. Thus, we have two different momentums. One is about regeneration, actually. The second is retraction, loss of mangrove. That's the difference between analyzing the two trends and one solid graphic. Of course, there is some influence of the non-homogeneous distribution of data, but even though, when compared to microwave papers, microwave-based analysis run by different researchers in different publications, they even with radar-based observation confirm that there are apparently two distinct moments of one, regeneration of mangroves or gaining of mangroves, and the second, loss of mangroves. In terms of mangrove regional distribution, we have Maranhão, Pará, and Amapá responsible for 80% of the Brazilian mangrove cover. And in terms of temporal persistence, which is interesting to analyze, we have 75% of the Brazilian mangroves that remained unchanged for 2 decades or more. So for 20 years or more, 75% of the Brazilian mangrove did not change. And some portion did change. 10% remained stable between only 1 to 2 decades, and 50% only for less than 10 decades. So it's a quite stable coverage, except from this fellow here, Amapá. Amapá is the state that shows the lowest stability of mangrove, but the reason for that isn't related to mangrove cover itself, but to atmospherical, noisy persistence in Amapá. The state of Amapá is the worst state, is the worst section in Brazil to be mapped using optical data. The degree of cloud persistence in the Amapá state is tremendous. So what we are seeing here is the optical classifier is struggling to correctly classify mangrove and not mangrove strata. So this is noisy influence. Want to work with Amapá? Switch to radar data instead of optical one. Great. Statistically, we've described our data, but we need to compare it with all the works. And that's it. In red is the reference used for the comparison. In blue, our data. What is in green here is what intersects, matches within one or the other. And we did this for 3 different references. The ICMBio Atlas, Mangrove Atlas, the Bunting et al. Team from 2008 using radar data, and Dr. Girichandra global mapping from the year 2000. And what we can see from here is that in all the 3 cases, the accuracy, the overall agreement is really high, 80% for the ICMB reference, 85% for the radar reference, and 87% for the method that uses the same sensor and the same resolution. And so I gave the tip to what can explain these differences. And here, the concept adopted by the ICMBio is the ecosystem mangrove. So they are considering, if you take a look into the left, even non-vegetative strata, the part of the ecosystem as mangrove. We don't do that. And for the radar, they've degraded their pixel values, their pixel dimension in the last output, because basically it's a global scale mapping project. So they are mapping more areas than we are because of the edges effect due to the increasing of the pixel size. Here, they are mapping more because of the ecosystem concept adopt. And we are really close to Dr. Girichandra data because both of us are using optical data from the same sensor with the same pixel, but I am capable of cloud filtering. Dr. Girichandra in 2000 wasn't. Google Earth Engine didn't exist. That's the difference between the absolute values. The reference states 4,000 kilometers square more than we do. The reference states 1.7 kilometers square more than we do. The reference states a bit less than we do, basically because we are capable of seeing behind the clouds due to the statistical capability of Google Earth Engine. Great. Nearly reaching the end of the presentation. This is the Article 2, largest scale deep learning approach for multi-temporal Aqua and Salicultura mapping. This was accepted this morning. Let's understand it. Here's the temporal variation of the Aqua, Culture, and Salines land use. And what we are seeing here has nothing to do with atmospherical or imprecise capability of optically mapping. Most of this data is concentrated in the northeast to south of Brazil. Therefore, cloud contamination isn't that complicated as it is in Amapá. What we are seeing here is that the economic attributes of salt and aquaculture, especially shrimp culture, created a boom in the beginning of the year 2000. And we actually started expanding our artificial coastal ponds. In terms of regional characteristics, 85% of the artificial ponds are grouped in only 2 states. Virtually everything in Rio Grande do Norte, a second portion of it in Ceará, and then things go reducing drastically. In terms of sector, we have 93% of aqua or salt production ponds related to northeast of Brazil, 6% to southeast with some importance of Rio de Janeiro, 0, none to the north sector, and 1% in south. So 93% is predominantly dominated by northeast region of Brazil. In terms of persistency, 55% of the aquaculture ponds are persistent in time for more than 20 years. It's a bit smaller than the mangrove persistency rate, but it's expected, as this is a use of land rather than a natural cover. So it's natural to be a bit more dynamic. Interesting findings, Maranhão presents 97% of its aquaculture pond to exist less than 10 years. And the signs of aquaculture activity in Maranhão existed only in the 80s. From the 80s on, it was abandoned and not activated anymore. Well, unfortunately, I have no reference data to cross-compare as I did for the mangrove mapping with multiple references, but we can always count on human interpretation. In this case, we performed an independent analysis where human users would, skilled, taught, experienced in coastal zone evaluation, were asked to tell me, out of those blue dots, which one it's over a aquaculture / saltculture area, which one is not. So it's pretty binary stuff, aquaculture, non-aquaculture. According to the cross-comparison between human-interpreted data and our maps, we have 94% of agreement for 1985 data and 91% of agreement for 2019, although there are still, as you can see, some margin to be improved. Considering the global error margin is about 9%, we still have some commissions and omissions to deal with, and here are some representation. Remember, UNAT is a contextual classifier, not a spectral or temporal one. Because this meandering river kind of did a 90-degree turn, the UNAT got confused and said, well, this is probably artificial. And because these two patches are close to the 90-degree angle, those two are probably artificial as well. Obviously, they are not. We need to better train our model so we can understand that this is not artificial, and either it and those two. And the opposite error also occurs sometimes. In here, everything there is this blue-greenish pattern is related to salt aquaculture use. So this spit here is fully dominated by aqua saltculture land use, although in this region here and in here, the classifier said aquaculture regions were not aquaculture regions. So this is a omission error. We need to better train our model to understand that either. Great. Finally, conclusion remarks. We've distributed this in 3 sections: global remarks, mangrove remarks, and aquaculture remarks. Global ones: the developed pipeline is reasonably scalable, sufficiently generic, and sustainable and suitable for large-scale mangrove and aquaculture identification. The developed spectral index, MMRI, proved to be robust, increased the spectral compatibility between the mangrove and non-mangrove strata. The data produced shows high levels of spatial statistical agreement. No less the reference is visually interpreted or cross-compared with other authors. Well, the approach allows systematic, continuous mapping of Brazilian mangrove, also of its aqua and saltculture ponds, filling a relevant gap of information, as this primary data in this spatial scale and temporal variability did not exist earlier before, and it's of fundamental importance for coastal analysis. In terms of mangrove remarks, 3 states, Maranhão, Pará, and Amapá, represents 80% of the Brazilian mangrove cover, and they are all in the north sector, what we call the Amazonian mangrove belt. 75% of the national mangroves, although, are unchanged, persistent for 2 decades or more, which is really positive. But then we need to deeply analyze what happened with the changing part. Although it's imperative not to rush the interpretation that the Brazilian mangroves are regenerating through time. There are 2 periods of distinct behavior. From 1985 to 1999, a downward trend of mangrove area cover, and from 2000 to 2019, the opposite. From 85 to 99, a upward trend, and from 2000 to 2019, a downward one. Finally, in terms of aquaculture and saline remarks, the 3 coastal states did not present any sign whatsoever of aquasouth patterns. They are Amapá, Pará, and Paraná. Maranhão presented the smallest detected amount of area, and the signs of aquaculture in this territory were present only in the 80s. From that point on, it was abandoned. 1985 to 1998 is a moment of stability where plus minus 5% of area variation actually occurs. On the other hand, from the beginning of the 2000 decade till 2019, a rapid growth marked an accelerated expansion of the aquaculture southculture ponds, which is in consonance with our economic parameters. Northeast sector concentrates 93% of the coastal aqua and southculture ponds. 2 states, Rio Grande do Norte and Ceará, represents 85% of such activity area. These findings basically are the first step to understand the influence of aquaculture and marine salt production might have on the coastal environment sustainability. Basically, that's all. The future developments will be expanded mangrove mapping to the entire South American continent, expanded aquaculture saline mapping to the entire Brazilian territory, and expand sandy surface mapping to include beaches, dunes, sandbars, sand strands of any nature to cover the entire Brazilian territory, not only coastal ones, and map the Brazilian intertidal environment. All the data produced in this research is available here and is already being accounted by the Map Biomas initiative. That's all. Thank you all very much.